The next talk is by Andrew Tofik from Amherst College, and it's titled Enumeration of Discrete Gradient Vector Fields on Simplicial Complexes. Uh, Welcome and go ahead.
Thank you so much. So my name is Andrew Tofik. I graduated from Amherst College back in January, and this was actually my senior thesis work with Yvonne Contreras and uh, Alejandro Morales. Studying discrete gradient vector fields, which are these objects in discrete Morse theory. So discrete Morse theory has been recently playing a fairly prominent role, being applied in quite a lot of places, most particularly topological data analysis on the subject of persistent homology. And it showed up other places as well, wherever essentially people care about homotopy types of simplicial complexes. But either way, in this talk, we'll mostly just be kind of in the realm of discrete Morse theory, proving things about discrete Morse theory. So to start off, let's recall what a simplicial complex actually is. So a simplicial complex on n vertices is just a collection of subsets of the set 1, 2, all the way up to n. So in this case, n is equal to 5. That is closed under taking subsets. So what I mean by that is, for instance, in this case here, so if we call this k, we have that 2, 3, 4 is inside k, and that represents this face here. And then closure under subsets means that every single subset of this would also be an element of k. Elements of k are usually called cells or simplices, hence the name simplicial complex. And every element of k has an associated dimension, and it's just one less than its cardinality. So for instance, this edge being consisting of 2, 3 would be said to have dimension of 1. And lastly, if you have some set inside K and then a subset of that set, you would say that that subset is a face of the larger set. And yeah, so these are just the basic terminology that we'll keep seeing again and again. So now moving forward, we can start kind of entering the realm of discrete Morse theory and talk about discrete Morse functions. So the definition is a bit rough to first look at, but essentially, it's an assignment of real numbers to every single cell of the simplicial complex, such that two properties are satisfied at every single cell. So for instance, let's pick a cell. Let's say this is going to be our cell sigma. The first property says that every higher dimensional neighbor of sigma, at most one of them can have a value less than or equal to the one at sigma. So if this is our sigma up here, its only higher dimensional neighbor is this one right here. And it has the value 18, and 18 is less than 20. And so this first set actually has cardinality of 0. So we're completely fine. Wait, actually? Okay, actually it has cardinality 1, but we're still fine. The second condition says that every lower dimensional neighbor of sigma, at most one, so every lower dimensional neighbor, at most one of them can have a value that is greater than or equal to the one assigned at sigma. So in this case, sigma has two zero-dimensional neighbors. Both of the values are less than it, so the second set does actually have cardinality 0. So we're fine there as well. Now there are cases where so essentially a discrete Morse function would be where these two conditions are satisfied at every single cell of your simplicial complex. But there are cases where for some of these cells, both of these sets might actually have cardinality 0. And these cells are very special. They're called critical cells. And they play a very, very important role in that we'll soon see that they tell us a lot of topological information about the simplicial complex. So we can check, for instance, really quickly at this edge here, that both 14 and 9 have value less than 30. So this set has nothing inside it. And since this edge doesn't have any higher dimensional neighbors, the first set also automatically has cardinality of 0. So this is the definition of a discrete Morse function. We won't be dealing too much with seeing all these numbers. We'll be mostly dealing with the gradients that they induce. So how do we get a gradient from a discrete Morse function? Well, here's the same exact function from before. And we start putting arrows down on our simplicial complex in accordance to this rule. We point an arrow from some cell to a neighboring higher dimensional cell if the arrow is pointing to something that's less than the cell essentially at the tail of the arrow. So if we look at this vertex up here, it has a value of 12. Its higher dimensional neighbors are these edges, and only one of them has a value that's less than 12. So we would get an arrow like this and kind of interpret that as saying that vertex is pointing to that edge. And then we'd go around and we'd essentially do this everywhere. So 10 is greater than 7, so we'd point downwards. Let's see, so 9 is greater than 8. And very quickly, just going around. So this would point to the two-dimensional face. And I think that's all of them. So you might notice some of them don't have any edges, and that they don't satisfy this constraint. I wrote it down on the bottom. And you might also notice that these are actually the same exact critical edges from just a slide ago. So that gradients tell us, and they kind of preserve this, preserves which cells are critical. So if two discrete Morse functions have the same gradient, they necessarily have the same exact critical cells. Also, this vertex is actually critical, and in this case, it is a sinc. And yeah, so this is how you get a gradient from a...
Can I interrupt you with a quick question? Or
yeah.
Can you explain again? So looking at the edge 20, like when do we get a flow into a face versus a flow, along an edge?
So the flow, so you have an arrow from, from a cell sigma to a higher dimensional neighbor tau. Let's see. So we would point an arrow whenever the value would decrease. So in this case, if we're looking at 20, so 20 as an edge can only point to two-dimensional faces. And the only two-dimensional face that is its neighbor is the one labeled 18. And 18 happens to have a less value, so it would get an arrow from it. But the reason we don't have an arrow pointing, towards 20 is that 20 has a greater value than both 14 and 15. And there's actually this theorem that essentially says, it's a result that's not too bad to prove, that every single cell is either the tail or the head of an arrow, but never both at the same time.
Yeah, great, thank you.
That's guaranteed by that cardinality condition.
Yes.
Of the Morse function. Okay.
So this is the gradient from this particular discrete Morse function. And now I can kind of explain why I keep emphasizing critical cells so much. So this is the main kind of topological feature we'll use of them, but discrete Morse theory gives us a lot to say about topology. So if we let Ci denote the number of critical cells of the function of dimension I, then we have these two conditions. So the first one says that the number of critical cells in dimension I is going to be greater than or equal to the number of, the ith Betti number. So down here, this is just a small variation of the one we had before. There are two critical vertices. So we have that C0 is equal to 2. And the connected components is just 1, and that's B0. So the first condition is satisfied. And then we can kind of check this for other dimensions. So we have 4 critical edges, and that is indeed greater than the 1, 2, 3 cycles that we have, which is 1. And then I suppose I should complete this. So we don't have any two-dimensional holes. And the second condition says the alternating sum of these critical cells is going to be equal to the Euler characteristic. And we indeed have that this is equal to the Euler characteristic, which is defined as the alternating sum of the Betti numbers. So these are very powerful, and they'll let us say quite a lot about the topology quite often, and they'll actually help us soon in trying to understand the structure of the gradients. So what is kind of like the goal overall of this talk? Well, the goal is to understand the number of different discrete gradients that can be placed on a simplicial complex. It's a finite thing. We'll only be looking at finite complexes. So there's only so many different ways of prescribing arrows, and only so many of them are actually gradients. So it turned out that in kind of trying to achieve this, what we end up finding is a connection to what's going to be called the Laplacian. So let me quickly define for you what the Laplacian is. And I need you first to recall that given a simplicial complex, we may associate to it a chain complex, which in our case, we're going to necessarily want these to all be Z modules. So they're all abelian groups. And in between these abelian groups, we have boundary maps. And the way the boundary map works, so here's a complex from before, where I've highlighted these two cells in the back and this one cell here. And the way the boundary map works, so if we take the second boundary map and we put in a subset of two-dimensional cells, so this is the purple bit highlighted, it'll just send it to its boundary. You did that right. Yeah. So in this case, this would be a graph on the right side, which I did not do right. There we go. Yeah, so we would send it to its boundary. And in this case, well, actually in all cases, the boundary of putting something inside a boundary map will necessarily send it to a cycle in one lesser dimension. And the image of things under the boundary map are called K-boundaries. And we can kind of interpret these boundary maps as essentially linear maps or matrices. And the nth Laplacian is defined to be the matrix product of partial n times partial n transpose. And in one-dimensional case, it's usually explicitly called the graph Laplacian. And yeah, and what we're going to find is a connection to the characteristic polynomial of the graph and in general of the Laplacian.
Sorry,
So this is our,
here?
oh, sorry.
Who's the graph in question? Because you have a simplicial complex. What is the graph?
Oh,
For the
so,
graph?
oh, sorry, what was that?
Sorry, what graph are you? You said it's going to be the Laplacian for a graph. Is it the Laplacian for a graph or for the simplicial complex?
So we're gonna essentially lead towards finding a connection to, in general, we're gonna show a connection to this, what is it, characteristic polynomial in general. But we'll start off with showing that, kind of proving this in the one-dimensional case. So given a graph, the gradients can, what is it, are kind of counted by the characteristic polynomial.
I see. So you're going to start with a simplicial complex that's just a graph.
Yeah, exactly.
Okay, thank you.
No worries. So yeah, so in one dimension, what is it? We start off with this nice, well, I should call it nice, but lemma, that there's actually a bijection between discrete gradients on a graph and rooted forests given by deleting critical edges. And we can kind of reason through this proof. So recall that the weak Morse inequality had this condition that C1 is going to be greater than or equal to the first Betty number. So that's essentially saying that kind of if you restrict your view to any single cycle in your graph, you're necessarily going to have a critical edge on its boundary. So if there's a critical edge on the boundary of every single cycle of your graph, then if you delete all the critical edges, you're necessarily going to be left with essentially a forest, a bunch of discrete trees. And furthermore, none of the, after you've deleted the critical edges, all these trees having Euler characteristic equal to 1 and no critical edges, the other weak Morse inequality says that there should be a critical vertex. And then just by the rules of a gradient, you're necessarily forced to point all your arrows towards that critical vertex. And that's how you get this bijection with rooted forests of your graph. And we can refine this and say this a little more precisely. In particular, if we kind of just partition our set of gradients into the ones having k-many edges, then we can just rephrase this lemma into saying that this set on the bottom is in bijection with rooted forest having e minus k-many edges. So I'm sure it might seem a tad bit silly that we went through the trouble of just kind of reformulating it in what seems to be a more messy way. But it's actually going to be very helpful, in particular in using the very kind of old theorem of algebraic graph theory. So there's this theorem by Biggs that essentially says if you have, that the characteristic polynomial of the graph Laplacian, its coefficients are given by counting the number of vertices in all forests of the graph having I many edges. So that basically says for Qi, fix a forest having I many edges, count its vertices, fix a different forest having I many edges, count its vertices, so on, sum that all up, and that's Qi. That's a bit hard to imagine, but this is kind of just equivalent to saying it's just the number of rooted forests having I many edges. And now hopefully it's clear why we did that rephrasing earlier, because then just immediately applying it says the characteristic polynomial of the graph Laplacian is actually just counting all these sets. And if we plug in lambda equals 1, what we end up getting is that we end up getting the number of gradients on the graph. Yeah, and these are all the number of gradients because all these sets are disjoint and their union is everything. So I will end the one-dimensional stuff by pausing on the slide here, which has this kind of done out for a cycle graph. So here's the graph Laplacian for it. Here's the corresponding characteristic polynomial. And on the bottom, I wrote out every single gradient you can have on the cycle graph. So yeah, if anyone has any questions, I will pause momentarily.
I don't want to interrupt too much, but I do have a question going back a few slides. If that's okay. Sorry, back. So here, yeah. So I'm confused. So here you have on the right in your rooted forest, you have 5 different vertices, right? 2 red ones and 3 black ones. And I guess this is a bijection, right? So I should be able to go to from the rooted forest back to the graph. And I don't know how I would know that there's that 6th vertex on the left.
Oh, so we would also have the knowledge that this is a rooted, we would have the knowledge of what this is a rooted forest of as well. So like we would be given the data that like, yeah, we would be given the data of like, this is what the forest, this is exactly the edges that you're missing.
Oh, I see. Okay. So you do know all the okay. Sorry, I was caught up on that. I was trying to imagine how to go backwards. All right. Thank you.
Yeah. Let's see. All right. So now we're gonna, move up in a few finite handfuls of dimension and talk about this in general. So kind of to try and motivate the result, let's try to imagine what would make sense for us to get. So the d Laplacian is the d boundary map and its transpose. So that's just the data of what's going on in d and d-1 dimensions. The d Laplacian does not know what's going on in anything less than that. So it shouldn't know anything about gradients or like arrows pointing to one another and lower than that. So we should in a way ignore that. So we should try and generalize the notation we had earlier to saying let ML of K denote the gradients on K, where essentially interesting stuff is going on in the dth dimension, but everything below that is critical in the sense of like, we don't have any data about what goes on in lower dimensions. So given a formulation like this, wouldn't it just be natural to think maybe it's the same exact statement? Maybe it's literally the same, it's phrased the same exact way. Maybe this exact statement is actually the characteristic polynomial. So we tested this with Sage, and we found that it worked for quite a lot of complexes, but then we found ones where it didn't work. And to explain to you why they didn't work, I will need to delve into rooted forests and higher dimensions. So let me explain what rooted forests kind of look like in 2 dimensions. So, so a forest in 2 dimensions, So a forest in 2 dimensions is a subset of the 2-dimensional cells such that, such that the second boundary map is injective. In other words, there are essentially no 2-dimensional holes. There are no cavities in your forest. Kind of like how in your forest in 1 dimensions, you don't want any cycles in the forest. And then the root of your forest is a bit more delicate in higher dimensions. In particular, you want it to satisfy two conditions. Oops. So the first condition you want it to satisfy is you don't want it to have a k-boundary. In other words, if you have a collection, if you recall, if you take just like a collection of two-dimensional cells and you shove that into the boundary map, then it's going to output this boundary here. And you want your root to be a subset of the one cells such that it doesn't have any of these boundaries. And you can see that's the case with all these cells highlighted in red. But secondly, you also want it to be, the case that if you ever add any more cells to your root, then you would have a k-boundary. So yeah, adding gives k-boundary. And you can see in these cases above, if I ever close up, say this right here, that now this is the k-boundary of these three cells. But that doesn't mean you can't have cycles. So for instance, over here, we have a cycle in here, but that's not the problem because that's not a k-boundary of any collection of cells. And yeah, over here, if we add like this to be a root, then it would be the boundary of this. So it is a nice generalization of what we had before. And and this is all due to actually Bernardi and Clevens. And they actually gave a very nice generalization of the theorem we saw earlier about how to express the characteristic polynomial of in higher dimensions. Sorry. Yeah. Yeah, so we do have a noticeably new key player, which is this term here, and that's due to kind of torsion becoming an issue in higher dimensions. So this does make things more delicate as we go up, and we'll see how this kind of messes around with things.
So should we think of that like a matrix tree theorem? Is that?
Yeah, or what is it? Well, what do you mean precisely?
It's an extension.
It's an extension of
An extension because it's explaining the entire characteristic polynomial. So one coefficient would be matrix tree.
Ah, okay. Okay.
So the next thing we'd want to do is we'd want to see if we can find again a bijection between rooted forests and gradients. So that's what we try and do. And we were able to succeed in this regard. So if you take a gradient and look at, define F to be the set of the non-critical D cells, and define R to be the set of critical D-1 cells. So this is very much just a generalization of what we were doing before. So here's a gradient on C4, the graph. This would be our forest right here. And then this would be our root. So in this case, we do get a rooted forest. But the sad thing is there's not going to be a one-to-one correspondence. In particular, there are some rooted forests that are kind of have these rough torsion and non-orientability issues where essentially there's no gradient that could possibly give it. But thankfully, we can say something, thanks to the work of Mukherjee of just not that long ago, that essentially showed that he was studying kind of like the homotopy type of these rooted forests, and he was using a lot of discrete Morse theory that was just very helpful. And he showed that if you have a triangulation of an orientable D manifold, then first of all, there exists discrete Morse functions, so there exist gradients. And secondly, this homological term is trivial, which we actually really needed. And therefore, we can finally end off with this, saying that actually this Laplacian statement does hold if we're talking about these. And in fact, we can also prove that for non-orientable D manifolds, triangulations of them, it necessarily does not hold. And but of course, actually, this doesn't mean consume everything. There are simplicial complexes which don't fall into either of these categories, which both some of them pass and some of them fail. So there's still much more to actually be said. But yeah, I think I will end here.
Thank you.
Thank you.
I have a question if there's time for questions.
Yeah, go ahead.
So when I've encountered Laplacians in the wild, I expect to see sort of two pieces, right? There's sort of an upper Laplacian and a lower Laplacian. Have you looked at that?
Yeah, so I think this is what you're talking about. It's usually, I guess, more written like this, right?
Yeah.
Yeah, so there's a lot of definitions of Laplacian, sadly. What is it? Oh, sorry, actually, this transpose is actually on the other side. But this Laplacian statement holds for both of these kind of halves, regardless where the transpose is. I've looked at the characteristic polynomial of this. It's hard. I haven't found a connection to discrete Morse theory. Yeah, I don't know much about this. I believe this bigger version is called like the combinatorial Laplacian. But yeah, I don't know of any connection to it.
Oh, that's a good question. So you say that if you have a non-orientable D manifold, then you can then this equation doesn't hold. But can you? Is there like a weighted? So in the Carly's theorem, right? There, if you require some weights on the rooted on the things that show up, right, coming from homology. Is some version of this theorem true if you allow certain weights inside of this sum?
Hmm.
Does that make sense?
Yes. Yes, it is.
Okay.
You have to, your weights also have to allow for cancellation. So it's an unsatisfying, yeah. Right there comes the combinatorial sort of stink.
Yeah, okay.
Yeah.
Thanks.
So yeah, whenever it doesn't hold, at least without weights and things, usually it's just off by the number of for each of the coefficients, it's off by the number of rooted forests that don't have a gradient. And I believe like if you're able to like fully characterize the exact rooted forest that I guess in the language in Carly's work, then if you're able to characterize the rooted forests that have fitting orientations on them that that don't have cycles, then yeah, you would be able to prove the whole thingy. But, yeah.
Thanks.
Can I ask kind of just a more general question? So you mentioned before discrete Morse theory has been used to compute persistent homology, right? So there's this is sort of how I've heard of it. I've never studied it particularly, but there's a Perseus software that was developed by Konstantin Mishaikov and Vedant Nanda, and they use ideas from discrete Morse theory to kind of make the computation of persistent homology efficient. And so I'm wondering, is there any desire or hope to use results like this to further improve that kind of computation?
I haven't closely looked at it, although I am curious how this kind of relates to current stuff. So there's another interpretation. So I believe like when it comes to computation with discrete Morse theory, a big kind of issue is so these gradients I mentioned are equivalently acyclic matchings on the Hasse diagram of the simplicial complex. And a big issue is the computation and kind of finding gradients is like there's like papers published just about the computational complexity of that. So I'm curious if this helps, or like how this could come into play in terms of kind of finding gradients, just knowing more of like the structure behind gradients, that they correspond in this way to rooted forests. But yeah, I currently don't know of yeah, any particular like immediate applications though.
Yeah, it seems like it might be, I don't know, you'd have to talk to an expert, but it seems like it might be applicable.
I also just wanted to add in one other comment, but I know we have to get to the next talk. So Kevin's Adinkras, the height function induces discrete Morse functions for surfaces that are supported on Adinkra graphs. So as a connection between these two, maybe I should just say that much, and then we'll talk about it in team flow and some of the breakout sessions for later. But so that's a place where these come into the physics story as well.
Carly, this is Jim. Thank you for saying that. I was having that same thought as Andrew was giving his presentation, that our height, our nodes actually have sort of an index that we call height attached to them. And this question of whether a discrete Morse function is important, we think has something to do with Lorentz symmetry in higher dimensions. We've seen evidence in some toy models in the past.
Okay, great. Well, let's thank the speaker again. Thank you.